In the vast reaches of space, where the cosmic tapestry unfolds across billions of miles, the Voyager spacecraft stand as emissaries of human curiosity and technological achievement. Launched by NASA in 1977, the Voyager probes were designed to explore the outer reaches of our solar system and beyond. As they journeyed into the interstellar medium, the need for software updates became apparent to ensure the probes could adapt, communicate, and continue their scientific mission effectively. This article delves into the remarkable story of Voyager's 15 billion-mile software update, exploring the challenges, innovations, and the ongoing legacy of these iconic spacecraft. The need for a software update. In 2015, NASA put out a job posting looking for a software engineer with a specific set of skills. The person had to be an expert in Fortran and Assembly 2 programming languages from the 40s and 50s that most young graduates don't know. Subscribe to the official channel of Technology Space. Visit their channel page and click the subscribe button and press the bell icon for more new updates. The job was to join the very small team of people working on the Voyager space probes. Incredibly, both Voyagers still run on their original 50-year-old computers, which have just 70 kilobytes of memory. It might not sound like much, but it was enough to navigate both space probes through our solar system and make incredible discoveries along the way. Unsurprisingly, things do go wrong with Voyager's computers. Just last year, Voyager 1 started sending back garbled telemetry data about its orientation in space. On top of that, the thrusters in charge of keeping Voyager pointing in the right direction were starting to show signs of fatigue. Every time the thrusters are used, tiny pieces of hydrazine fuel get stuck in the pipes. This has built up over time, causing blockages in the system. Voyager is already on its backup thrusters, and so if these failed, it would be the end for Voyager. At a distance of 15 billion miles, there is no way of clearing the tubes, but in order to slow down the buildup and fix the telemetry problem, the small team in charge of Voyager began writing a software update that would be sent across our universe to fix it. There are 3 main computers on board Voyager. The main computer controls all of the major instruments, maintains its health and temperature, and also controls the other 2 computers. The second computer is in charge of Voyager's orientation, so it looks for predetermined reference points and fires the thrusters to keep Voyager's antenna pointing towards Earth. The third computer is in charge of storing and handling all of the scientific data and images taken by Voyager's instruments. Voyager doesn't have an operating system, and any kind of programming language would take up too much space, but this isn't the first time Voyager has been updated. At Neptune, the light was 900 times dimmer than it was at Earth, so in order to take pictures, engineers had to reprogram the camera to take longer exposures. Once it left Neptune, NASA began shutting down things like the camera and various scientific instruments to save power, but with just 70 KB of memory on board its computer. Having lines of code for dead instruments was a waste of space. And so the engineers completely rewrote Voyager's code and performed a software update to make sure it continued to live for the foreseeable future. But how does NASA update such old hardware from 15 billion miles away? To understand how difficult this is, we need to know how the software works on Voyager. The update process. In order to do a software update on Voyager, NASA needs to install the new code into its computers. Perhaps the coolest thing about Voyager's computers is the memory. Each computer has its own plated wire memory, which stores Voyager's code in its most basic form, 1s and 0s. This memory consists of a physical grid of wires and thin metal plates. Each intersection point can be thought of as a single bit of memory, and it can store either a 1 or 0. By passing a current through one of the plates and a specific wire, it would create a magnetic field. If the magnetic field is in this direction, it is considered a 0. If it goes in the opposite direction, it's a 1. By passing a current in the opposite direction, it would change the direction of the magnetic field and flip the bit to a 0. By doing this for every point, you could save these ones and zeros into the memory. This design was a great choice at the time because it meant that even if the power went out, the ones and zeros would still be saved to the memory. It also meant that each bit could be updated. With just 70 kilobytes of total memory on board Voyager, the engineers have to be extremely efficient with their code. Along with this basic machine code, Voyager has its own pseudocode, basically a series of shortcut commands that can be triggered to carry out repetitive tasks without taking up too much memory. An interpreter on board the main computer reads the ones and zeros. Once it comes across a predetermined code, it initiates the pseudocode to carry out a command. This saves lots of memory and allows many tasks to be automated without writing out long lines of code. But the problem is that humans can't code in just ones and zeros. And so a more advanced language is needed to actually write the code for Voyager. On Earth, Voyager Software was originally written in assembly language with a little bit of Fortran. Assembly is a very simple language that can be understood by humans, but is much closer to the basic ones and zeros of machine language. Once the code is complete, it gets compiled into machine code, which can be sent to Voyager using the Deep Space Network. The data is sent to Voyager at a rate of 16 bits per second, and it takes almost an entire day to actually reach Voyager. The computers on board Voyager are interrupt-driven. This means that the software goes through its usual list of instructions until it gets interrupted. When an update is sent to Voyager, it carries an interrupt signal. When Voyager receives this, it tells the main computer to stop what it's doing and instead work on the update instructions. It then unloads the new code into the memory, flipping all the bits to their new position. The code is then read through to check that everything is correct, and then the main computer kicks it into gear and returns to normal operations. Over the years, Voyager has received a long list of updates and patches to fix and improve how it operates. In 1995, an update was written that would basically restart certain components if they failed. In 2014, some 20 years after the code was written, this code saved Voyager 1 when a piece of hardware malfunctioned. In 2010, a single bit of Voyager's memory was flipped, changing a 0 to a 1. This caused computers to lose sync with each other, and the commands started happening 2.5 hours later than expected. A software update was sent up to flip the faulty bit back into its correction position. It's amazing stories like these that have allowed these iconic space probes to survive almost 50 years in space. It's incredible that the physical wires, transistors, and hardware onboard Voyager's computers are still operating as intended after all this time. In conclusion, Voyager's 15 billion-mile software update stands as a testament to the ingenuity and determination of the teams involved in the mission. The successful adaptation of software to meet the evolving needs of the spacecraft in the harsh conditions of interstellar space showcases the remarkable capabilities of human space exploration. As Voyager continues its odyssey into the cosmic void, it leaves an indelible mark on the annals of space exploration, inspiring future generations to reach for the stars and push the boundaries of our understanding of the universe. A heartfelt thank you to our amazing viewers and supporters of Technology Space. Your enthusiasm for space exploration fuels our passion. We appreciate your continued